All right, students. We're going to start vodcast 2.5. We're going to talk about kinetic molecular theory, and I just want to apologize at the beginning. I don't have the pen with me, so I'm trying to pop stuff in as best as I can. So video's a little sparse compared to the stuff that we're usually watching. What is kinetic molecular theory? Kinetic molecular theory is sort of the heart of how we treat the way that molecules and atoms move, and we're going to talk about specifically in how it relates to phases. So the first part of this is that kinetic means things that are in motion. If you're riding a bike or if you're running, if you throw something, it's in motion, or we would say that it's moving. Molecular obviously means that we're referring to molecules. Okay, so molecules are the things that make up matter. Atoms make up molecules. Molecules make up most matter. That's sort of the basis, fundamental part of matter that we've been talking about. And so if we took the idea of kinetic molecular theory, we could sort of change this to the moving molecules theory. Okay, basically saying that just keep in your mind that everything that we're going to be talking about is about molecules in motion. And this is basically what we mean. Basically, molecules are always moving, and if you get a quick look at this diagram as the animation is going around, you'll see sort of the gist of kinetic theory as we're going to talk about it. We're going to treat atoms or molecules as though they're little tiny spheres. They're constantly moving around. If you look at this video, they're bouncing off of each other. They're not really gaining or losing too much energy. You'll see some of them slowing down here in this video, and that's a little different than the kinetic theory that we're going to talk about. But basically, just that molecules are always moving around. And so kinetic energy, if things that are kinetic have motion, kinetic energy means energy of motion. And you probably remember this back from middle school science class where you talked about potential energy and kinetic energy, or maybe if you've taken physical science. And so there's a formula to calculate the amount of kinetic energy. And the formula here is that kinetic energy, the Ke, equals 1/2 m times v squared. Okay? The m is the mass in kilograms of the particle, and obviously if we're talking about molecules, that mass in kilograms is going to be incredibly small. And the v is the velocity of the particles, or the mass, meters per second that they're traveling. And then we're going to square that. And so if you multiply all that together, you would get the kinetic energy. Now, we're not going to very often actually plug stuff into that formula, maybe once or twice in the semester, but you need to know that that's what the formula is, just in case that happens to pop up at some point. So basically, there are 5 points or 5 pillars of kinetic theory. So kinetic theory is held up by these 5 ideas. And what's really important to realize about these 5 ideas is that they're not all necessarily, I don't want to say they're not true, but they don't hold true in all cases. Okay, so just sort of keep that in mind as we go through them. So the first one, sorry about that pop in down there. The first one is that molecules are small hard spheres. Okay, and so if we take our little diagram here, okay, and just make it a little bit bigger, we're going to act as though the molecules are just these little tiny, basically sort of like billiard balls. You can sort of think of them as that's sort of the classical model. The gas molecules are in constant random motion. Okay, they're always moving around, bouncing all over the place. The third one is the one that's not really shown that well in the diagram, but it means that all collisions are elastic. And if you watch the pop-in here, it should help you out with that a little bit. But elastic in the sense of molecules doesn't mean stretchy. Elastic means that energy gets completely transferred. Okay, so that if they run into each other, they don't lose their energy. The energy gets transferred from one particle to another. That doesn't matter a whole lot to us at this point, but just keep in mind that idea that we're not losing energy as they hit things. The fourth point is that there's no attraction or repulsion between the particles. Again, in reality there is, but we're going to treat them as though they're not because the calculations get a lot more complicated if we do. And we could do that in AP Chemistry next year. We'll talk about some of how to put into the calculations some of that attraction and repulsion. But for now, we're going to pretend that they don't. And then the last part is that temperature is a measure of the average kinetic energy of the molecules. Okay, we're going to talk a little bit more about what that means. So if we look at this diagram here then, this is what is called a Boltzmann distribution. Okay, I'm going to bring this up and just make it just a little bit bigger so we can kind of key in on it just a little bit more. But what a Boltzmann distribution is if you look on this side, it shows the number of molecules, and then on the x-axis it's speed, and so it's speed versus number of molecules. And you'll notice that each of these three lines has a different temperature attached to it. So 0 degrees Celsius, 1000 degrees Celsius, 2000 degrees Celsius. And what the Boltzmann diagram does, sometimes it's called a Maxwell-Boltzmann distribution. There's a whole lot of complicated math that goes into it that we're not going to do. But the basic idea is that the average amount of energy of the molecules, okay, at each stage is shown by this diagram. And so if you look at the red diagram, you'll see that that most of the energy is sort of down here in this lower part. Okay, it doesn't mean all of it. Okay, but that's sort of the average. There are some molecules in the red, okay, like down here, that have a lot of energy, okay, or a lot of speed. Remember, speed basically means energy to us. And there's quite a few that don't have very much, okay, that's really low speed. So high speed over here, low speed here, okay, and the average is somewhere in here. So at a temperature of 0 degrees, the average molecule has kind of a low speed or a low kinetic energy. If we went then and looked at 1000 degrees and we looked at the average there, we see that the average is much higher. Now, the low molecules for 1000 degrees are about at the average of the 0, okay? And then the high energy molecules have a lot higher energy or speed than the highest of that red line of the 0 degrees. And then if we went to another temperature, we see that the average there, or the midpoint at least, for 2000 degrees is even higher than it was for 1000, and that the slower molecules, okay, are moving about as fast as the average was for 1000. And then we've got molecules that are moving way, way faster. Okay, so what does all this mean to us? Well, essentially what this means then is that the speed of the molecule is determined by the temperature, or rather, I guess to state that more accurately, the temperature tells us a lot about the speed of the molecule, that the higher the temperature, the higher the speed. And so if we look here at oxygen and we look at the temperature, so oxygen at 300 Kelvin, the molecules are moving at an average speed of 480 meters per second, which is really super fast. And at 400 Kelvin, they're moving at 560 meters per second. So in other words, when someone asks what's the difference, what does temperature mean as far as molecules go, it means the higher the temperature, the faster the molecules are moving, the more kinetic energy that they have. And that's what that Boltzmann distribution shows us. And just to get a little bit of idea, everything we've talked about so far essentially holds true for gases. But we're going to talk about in all of this stuff more than just gases. We're going to talk about liquids and solids as well. So to get a little bit of an idea of what that looks like for liquids and solids, I want to pop to this little website here. And they're going to pop through some notes, and you guys can jump to this website. It's preparatorychemistry.com. But here's what I want you to look at. Okay, look at this diagram. And so right here, we've got a bunch of molecules sort of packed together. Okay, this is what they look like as a solid. Okay, and if you take a real quick look at this, you'll see that none of the molecules, they're all moving, but they're not really moving around each other. They're kind of vibrating in place. They're bouncing off of each other. You see this little ball in the center? He doesn't really get to move. He gets bounced off of the other molecules, but he never really shifts his overall position. It's always right in this general area. If we go to a liquid, okay, we'll see that the particles are moving much faster. And it's kind of hard to visualize in this example, but what actually starts to happen is this little black ball starts to slip around the other ones a little bit. He's still in the same general location, but he can move around. And you can see that overall, they're going to start to slide around each other. Okay, and so this is actually the better liquid one. You see that little ball is moving all over the place. He's sliding through all of them. Okay, back just a minute ago, that was actually the fast, higher temperature solid where they're moving a little faster. Here, they're in the liquid, they're flowing. Okay, the molecules are moving around each other. Okay, now here, this is an example of a liquid, and at the top, you see some molecules starting to escape. Okay, and if you see the picture of the flask down here, okay, right at the surface, that's what we're showing here. Right at the surface, some of those molecules escape out. And what do they escape into? They escape into gas phase. We see here, this is sort of a diagram of what gas phase molecules look like. And in the gas phase, the molecule, you'll notice that in this same little frame that we saw the others, we don't see many molecules. And the ones we do are moving really fast, and they're moving past each other, and then they're bouncing into each other. That is kinetic theory. Okay, small hard spheres, constant random motion. They're really far apart from each other. They're bouncing into each other and projecting that energy off. Okay, so just real quick, that's gas phase. Okay, liquid phase where they're flowing around each other, and then solid phase where even if it's a hot solid and they're moving around, they're still locked into position. They're basically vibrating in one place. Okay, so hopefully that gives you a little bit of an idea of what's going on at the molecular level. And remember, that's what kinetic molecular theory is all about, is what's going on at the molecular level for these things. Okay, so a couple of diagrams I want to show you before we end the vodcast. The first one is that we have this continuum here of kinetic energy. Okay, and as kinetic energy goes up, we change from phase to phase, and so we're in solid phase here. And as the kinetic energy increases, we get to this barrier. Okay, and if we can get across the barrier, we turn into a liquid where the molecules are going to flow again. And then if we keep increasing the kinetic energy and we get across the next barrier, then we turn into gas phase where the particles are moving really far apart from each other. Now, what does this mean to us like in an everyday sort of situation? Well, it has everything to do with temperature. Okay? Remember, temperature is a measure of the average kinetic energy of the molecules. So as we go from solid to liquid to gas, we're increasing the temperature. Okay, and that's really useful to us because what we'll see in the next vodcast is that we can use those temperature calculations to actually figure out the energy involved in these things. Okay, and one quick last thing I want to show you in this vodcast is that all of this is then going to relate to this idea of phase changes. Remember in the last vodcast we talked about phase changes being a physical change. Okay, and so there are all these different phase changes from solid to liquid to gas. And so we've got freezing and melting, condensation and vaporization, and then sublimation and deposition as we're changing phases here. Okay, so all of these phase changes, and remember in each case what's going on is an energy change or a temperature change. We'll find out later on this year when we talk about gas laws that it's not just really a temperature change, that there's pressure involved as well. But for the most part, temperature is a good measurement of the average kinetic energy of the molecules. All right, thanks guys, and we'll see you again soon.